In this screencast, I'll show you how to solve for the conductive heat transfer rate through a composite wall as shown below. In order to solve using our thermal circuits, first of all, we have to assume that the surfaces normal to the x direction are isothermal. So instead of having a straight thermal circuit, we're going to have something that looks like this. So we have our heat transfer rate in the x direction, and we start with our T1, which is the T on the first outside wall. The first resistance that it goes through is the conductive resistance through section A. We have L sub A divided by K sub A, and then our area of A. Then we get to a point where the wall splits into two sections of different lengths as well as different materials. However, instead of continuing with a straight line, we split this off so that there's one resistance that goes with wall B and one resistance that goes with wall C. And these resistances are conductive. And keep in mind, when we talk about area, we're talking about that cross-sectional area that our flux goes through. Then we end up coming through our final part of the wall that we'll call D, and it has its own conductive resistance. And then the end of our thermal circuit is this T2, which is the temperature, the outside temperature of the final wall. Our thermal resistances are therefore going to be written such that our first one, LA, divided by the thermal conductivity and its area. Then we'll look at the last one, LD, divided by its thermal conductivity and area. However, because the wall splits, we can't write our resistances in the same fashion. And so the way we write it is that we have the inverse, KB, or 1 over the resistance, times its area divided by its length, plus, again, the inverse of its resistance. And we then take the inverse of this sum in order to get what we consider an equivalent circuit. So let's use the following values to calculate our heat transfer rate. Notice that the areas change for both B and C because if you look up here, the height is different for each one of them. The sum obviously is going to be 1 meter, but one of them has a height of 0.4 meters while the other has a height of 0.6 meters. So let's use now this information to find our resistances. So we'll first find the resistance of A. That's our L, 0.5 meters. We divide that by our K, 0.038 watts per meter Kelvin, times our area, which is 1 meter squared, and this is going to equal 13.2 Kelvin per watt. Our RD will calculate the same way. So its resistance is 17.5 Kelvin per watt. However, now we're going to have to put an equivalent resistance for B and C. And so what this is going to equal is, for B, 0.12, here's our thermal conductivity, watts per meter Kelvin, and this is multiplied by its area. And notice that this is just the inverse of the resistances we wrote before, obviously with their own numbers. And so we do the same thing for our C. And so when we calculate this, what we call equivalent circuit, we end up with 0.47 Kelvin per watt. If we want to calculate the heat transfer rate, that's just the difference in temperature divided by the sum of these resistances. So that's going to be 55K divided by, now we just sum these all up, 13.2 plus 17.5 plus 0.47, and these are all in Kelvin per watt. And when we calculate this, we end up with a heat transfer rate of 1.76 watts. So if you notice here, instead of us being able to use our standard thermal circuit where we just sum up all of the resistances, because of the split in this wall right here, we're going to have to create an equivalent resistance for those two parts of the wall and find our heat transfer rate using that.